So, welcome once again to this course on convex optimization, and today we are going to speak about some very important aspect of convexity, the differentiability of convex functions. Now, the first question is whether every convex function is differentiable or whether it is continuous at all, or is there something else. So, first question is every convex function continuous? As every differentiable function is continuous, so we will at least know that okay, if a function is not continuous, it is not differentiable, of course. So, is every convex function continuous? The answer is surprisingly nice, because here if you take a function from Rn to R and if f is convex, then f is continuous. So, this is something quite interesting, but if you take a function f from C to R, where C is a closed convex set or a convex set, you need not bother about closed, I am just bracketing it, then f may not be continuous over whole of C. Let me take this very simple thing. Let us look at a function like this, and let us take this C as 0 plus infinity in the real line, and I define a function like this. So, okay. Say this is just f x equal to x s square for x greater than 0 and is equal to half for x equal to 0. So, this is half, this is a 0.0 half. But if you look at the epigraph of this function is discontinuous at x equal to 0, but if you look at the epigraph of this function, the epigraph of this function is obviously convex. The epigraph is obviously a convex set. So, it is very clear that f x f is a convex function on C equal to 0 to infinity, but is not continuous. So, with this basic idea, let us come down and consider the case when f is from Rn to R and f is differentiable. Then you can characterize convex functions through this through the basic notion of a gradient, that is f is convex if and only if f of y minus f of x is greater than the gradient times f of x into y minus x for all x y in Rn cross Rn. That is for all x y in Rn. Now, I guess I have already proved this fact once earlier, but let me just recollect and do the proof. The proof of this fact is absolutely simple. It relies on the notion of convexity. So, if a function is convex, you write lambda y plus 1 minus lambda x is lambda times f of y plus 1 minus lambda times f of x for all lambda lying between 0 and 1. Of course, it is including 0 and 1, but okay, it is of course true for every lambda between 0 and 1. So, now you can rearrange this, and write this as f of x plus lambda times y minus x, and that is less than lambda f y. Now, if you look at this one, then transfer one f x to the other side. So, if it f of x plus lambda y minus x minus f of x is less than lambda times f y minus f x. Now, differentiability would again allow us to expand this thing in the form of a Taylor's theorem, and that would lead to grad of f x lambda y minus x plus small o of lambda is less than lambda times f y minus f x. So, this would imply that grad of f x lambda times y minus x plus, so we will divide by lambda, because lambda is between 0 and 1, we can divide by lambda and we can have this. Now, this will immediately show us something. It will immediately show as lambda goes to 0, that is lambda is positive and goes to 0, this will go to 0. It will imply that f of y minus f of x is greater than equal to gradient of f of x times y minus x, right. Now, let us look at the converse. If f is differentiable and it satisfies the following, if it satisfies the following, then f is convex. So, I would prove it, but I am just going to give a hint of the proof. The hint is as follows: consider z, or maybe I will just do the proof. Consider z as lambda y plus 1 minus lambda x, where lambda is something number between 0 and 1. Then, if this is what it is true, then f of x minus f of z is greater than gradient of f of z into x minus z. Similarly, you can have f of y minus f of z is greater than equal to gradient of f of z into y minus z. So, your job would be to add this, multiply this with 1 minus lambda, multiply this with 1 plus lambda, and once you do this, when you add up, you will simply get that f of z is less than equal to lambda times f of y plus 1 minus lambda times f of x. Okay. Now, So, this operation was 1 minus lambda into this equation and lambda into this equation 1 minus. So, multiply with 1 minus lambda and here multiply with lambda and then add up this to get this result, and z you know is what, and so that is convexity exactly. Now, the question is every convex function differentiable? So, how do I answer this question? The answer is no, because just look at the most well known convex function which does not have a derivative, that is f x is equal to the absolute value of x when x is in R, and at x equal to 0 is the point where the function does not have a derivative, and also it is the point where the function attains a minimum. And in fact, most functions which are not differentiable attains a minimum only at the most convex functions which are not differentiable precisely attains the minimum in the place where the derivative does not exist. So, this property of convex functions which are not differentiable, for the property of minimum being attained at non differentiable points, is a generic property, and it works for all convex functions, almost all. That is the meaning of genericity in a very loose term, but okay. So, the question is what happens if I do not have differentiability? That question we will answer slightly later, but let us show that the convex functions can also be characterized through the notion of gradients through an interesting property called monotonicity, and currently there is a huge study on the relation between monotonicity and convex functions. This is a huge research topic and it is worth exploring. So, let us look at the notion of monotonicity of gradients. So, look at the convex function, take a convex function f from R n to R is convex and differentiable. Now, then I can take it to n into x y, let me choose n into x y, whatever I want. Then I can write f of y minus f of x is gradient of f x into y minus x, and then I can also write, just by swapping the positions of x and y, this inequality is also true, because that inequality is true for any pair x y. So, if I call this equation 1 and I call this inequality 2. So, if I add up 1 plus 2, what I get is 0 is bigger than grad of f x into y minus x plus grad of f y into x minus y. So, this would immediately show that grad of f y minus grad of f x into y minus x is greater than or equal to 0, and this is the monotonicity property of the gradient. This property is called monotonicity. Now, we must also show that why it is called a monotone property, because we are dealing with vector functions which are vector functions. Note that you take any function which is increasing, say just in R to R, take a function from R to R, need not be convex, here I have not drawn a convex function, which is increasing. Increasing or non decreasing, basically take if this f is non decreasing, more fashionable term. Increasing is what one would call strictly increasing. This means that you have x lesser than y, f of x must also be lesser than f of y. Now, if you look at this, this would imply that f y minus f x is non-negative, so is y minus x. So, the product is also non-negative. So, this is actually generalized to this setup, because here we have vector functions. So, instead of multiplication we have inner product, as we know inner product is a generalization of the notion of multiplication in vector spaces. So, this that is why it is called monotonicity property, it is coming from the increasing idea. Okay. Now, of course, we have already proved this fact, which we are not going to prove, that if f is a twice continuously differentiable convex function, so twice continuously differentiable, that is symbolically f can be written to be in C2, twice continuously differentiable, then f is convex. So, this is what I am repeating, I have already proved it. If and only if the Hessian matrix is positive semi definite for all x. Now, you might be curious, I would have asked this question, okay, the gradient satisfies this property, what about a differentiable functions whose gradient satisfy this property? Is it a convex function? That is the question. Let us figure it out. So, now I am given f differentiable and for any x y this is given to me. Now, let me look into this. See, what I have to do to prove that a differentiable function is convex is to show that that is my job now, to show that f is convex. So, my question is f convex? That is my question. So, to show convexity, I must show something like this. Of course, because the function is differentiable, it is enough to show that this is true, because this is for any pair x y. So, this is all, this result would be for any pair x y. This is what I have to show. Now, my question of course is, can I show that? To do this, I will use the mean value theorem. Now, what does MVT does? So, if you remember, for functions from Rn to R, the MVT is where Z and is an element of the open line segment between x and y, that is Z is written as x plus lambda y minus x, where lambda is strictly between 0 and 1. So, there is some lambda. So, there is a lambda between 0 and 1 such that this z can be written like this. Now, if I write it like this, I would have immediately f of y minus f of x is equal to the gradient of z is x plus lambda y minus x into y minus x. So, this is nothing but greater than. So, if I subtract out x, so now let me look into this. Okay. Now, I will use this monotonicity property fairly well. What I will do is I will prove the following. I will see that if you look at this f of the gradient of f of x plus lambda y minus x minus the gradient of f of x into the difference lambda y minus x, this by the monotonicity property has to be greater than equal to 0. I can obviously take the lambda out and divide by lambda, because lambda is between 0 and 1. So, I would immediately have the fact that grad of f of x plus lambda y minus x into y minus x, the inner product is bigger than grad of f of x into y minus x. So, now I can just leap it up and show that this is nothing but greater than grad of f of x into y minus x. So, what does it show? F of y minus f of x is bigger than grad of f of x into y minus x. This is exactly this fact, but since x and y are arbitrary, so this is true for any x y, thus showing that the function is convex. Now, the next question is what happens if f is not differentiable? Can we do anything about it? Just take the diagram of this and try to play with it for a while. As I go on speaking a bit more about how much I can play with the derivative from an optimization point of view. That is okay. Now, if f is, I will talk about this after some times. So, I give you a little time to play around. Take this non-differentiable function and see that because here there is no derivative, your standard f dash x equal to 0 type technique will not work while trying to figure out the minimum. So, which means that there must be some way by which one can figure out the minimum. So, if that is so, then what should be that way? So, can there be something which replaces the derivative in this scenario? I will give you some time to think and play around, but then let me tell you something bit more about differentiability of a convex function and optimization. So, if f is from R n to R and is convex, then any local mean is global. For example, so if x is local, then we have proved then grad of f of x is equal to 0, is a local mean, sorry. Then by using the convexity inequality for any y, once I fix the x for any other y, you can always write this. Now, once you plug in grad f x equal to 0, that will give you 0. That will show that f of y for all x, sorry, for all y, So, showing that f x is a real minimum. Now, this also triggers this expression f y minus f x is greater than equal to grad f x into y minus x. This also triggers a slight generalization of the notion of convexity, because if you observe, if I take this, then what do I see? I see that f of x so whenever this is greater than 0, f I is greater than equal to f x. So, this would imply the definition of the so called pseudo convex function. Every convex function naturally would be pseudo convex, but every pseudo convex function is not convex. So, let me just give you, this is just for slight detour, but we will just not bother about these functions anymore. F is pseudo convex if whenever we have grad of f x into y minus x is greater than 0, it should imply f I bigger than f x. For example, if you take the function f x equal to x cube plus x, this is not convex. Of course, x here is in R. This is not convex, but pseudo convex. From the mid 70s to mid 80s, also even lately in the 90s and some in the current decade, there have been a vast amount of work on pseudo convex functions and how they are applied to areas like mathematical economics have been explored. So, now once we know a bit about this going beyond convexity, but we will just scale back ourselves to convexity, because it is not so easy to detect functions in Rn to R which are of this form. So, we go back to our standard convex functions again, and here now we talk about this problem, minimize f x subject to x element of C, which means that here I consider f to be a convex function and C to be a closed convex set or just a convex set, and I will consider f is convex and and also differentiable. Now, the question is, can I write a necessary and sufficient optimality condition? You have observed that every local minima is global. So, once you have a local minima, the necessary condition is grad of f x equal to 0, this is necessary, but once the function is convex, it is also sufficient, because once I have this, I know that this corresponding x is the optima. So, similarly, I am coming to this question. So, now if I take a global minimum of this problem, because of any convex function over a convex set, if it has to be minimized, every local minima is global, that you already know. So, is there any characterization in terms of the gradient and in terms of elements of C which would be always giving me a necessary and sufficient condition? So, how to do this fact? So, now begin by consider x bar to be a global minima of this problem, which is the standard convex programming problem CP. X bar to be a given global minimum CP. I am writing global in the bracket because it is always global minimum. Now, take any x in C, then x bar plus lambda x minus x bar is element of C for any lambda which is between 0 and 1, strictly lying between 0 and 1, obviously any lambda between 0 and 1. Now, because this is in C and x bar is a global minima, so I would have f of x bar plus lambda x minus x bar to be bigger than f of x bar, right. Once I have this, so I can repeat that thing, f of x bar plus lambda x minus x bar. So, here from here I will take it to this side to write this as. Now, once I know that the Taylor's or the function is differentiable, the Taylor's theorem would be invoked, or rather the definition of differentiability would be invoked to give me this expression. Now, I have taken lambda, this is true for whatever lambda you take between 0 and 1. So, I can now divide by lambda on both sides because lambda is a positive quantity. So, I go on dividing by lambda, which would lead to an equation of this form. So, as lambda goes to 0, we have now you see this is true for any arbitrary x of C I have chosen. I have not chosen any particular x in C of particular structure, just an x in C. So, this would imply, since x is arbitrary, x element of C is arbitrary, this above condition this condition, though looks analytic, is actually a geometric condition, but we are not in a position to tell you what is that geometry. So, the beauty of optimization or convex optimization lies in the interaction between analysis and geometric, analytic notions and geometric notions, and on one hand, and the beautiful interplay of matrices and optimization. These are the hallmarks of convex optimization, and it's truly exciting. And for anyone who wants to enter the field, this is one of the high times, and because the field is growing at a very fast rate and a lot of exciting things are coming up. And now, the question is, so I have a necessary condition, I have taken x bar to be a global minimum, and then I have figured out this is what x bar should satisfy. So, now, what about sufficiency? Let x bar element of C be given. Now, let x bar element of C be given, and for any x in C we have. So, this is what is the reverse we are asking for. The question is x bar a minimum of CP? The answer is yes, because you can immediately see because then you know f of x minus f of x bar by differentiability of the convex function So, I have just said that this is given to be greater than equal to 0 for all x in C. So, which would immediately imply that f of x So, the necessary and sufficient condition is the following. So, x bar is a global minima of a convex programming problem CP if and only if this holds for all x element of C. So, this particular sort of representation of a necessary and sufficient optimality condition for a convex minimization problem, minimizing a convex problem over a convex set C, is usually termed as representation via variational inequality. Now, this problem you see grad f, if you observe, is a vector function from Rn to Rn. Now, instead of this, if I choose some arbitrary vector function from Rn to Rn and I pose the question, find x bar element of C such that where C is convex, the same C, such that grad of f of x bar x minus x bar is greater than equal to 0 for all x in C. So, this is what is called a variational inequality. Or VI problem, usually denoted as VI F and C. So, our convex programming optimization problem can be also written as a VI grad F C. So, this is nothing but our convex optimization problem. You know, if I have a convex optimization problem, so the set of all global minima of F, set of all global mean of F can be written as, or usually written as, arg mean F, the argument at which means the x values for which F attains the minimum, arg mean F, the set of all x in C such that f of x is equal to mean of F. This is what is called arg mean F. Sometimes people denote it by C to say that okay, I am. So, this is a set of all global minima. Now, of course, when F is convex, this is a convex set. How will you prove this? Very, of course, you can use convexity and then try to prove this, which is very simple, convexity of F. The another way to look at it is that if the function is differentiable, what would happen? Then suppose x is in C and then you know by differentiability we are invoking the monotonicity property, if x bar is the optima, that is x bar is an arg mean C, then this is what I have for all y in C. So, this would immediately imply now by the necessary and sufficient optimality condition I know that this grad of f x bar into y minus x bar, this is greater than equal to 0. This is exactly what we have just, this is exactly what we have just studied, this one. So, which would imply that grad of f y into y minus x bar is greater than equal to 0. So, So, you see this is an alternative way of looking at the necessary and sufficient optimality condition, that is a convex function f has a global minima at f if and only if this is true. So, the argmean of f can also be written as, it can also be written as grad of y belonging to C Now, each of these for a fixed y, each of these is a convex set. It is very simple to see this. So, if you take intersection of arbitrary number of convex sets, you get a convex set. So, argmean f c is convex, this is another way to look at it, and this is a alternative optimality condition. So, these are all interesting areas which one can look into. This leads to what is called the Minty variation inequality. We would not get into those things at all. So, this is one alternative. So, you see, if a convex function is differentiable, I can use the gradient to represent the optimality condition. So, it is representation of through so, if my f, the convex function is differentiable, I can use the gradient itself, gradient of f itself to represent the set of all global minimizers. Representation, here I am representing it through optimality conditions, sorry, representation through gradient by gradients, not optimality conditions, sorry. So, optimality conditions can be used in fact to represent the argmean itself. So, there are two, so this argmean can have this representation. So, two different ways of representing it. Now, I will show you something interesting. I will try to employ what we have just learned, this optimality condition, in one particular case. Consider, and we will end today's lecture with this. Minima is half. So, I am talking about a quadratic programming problem. X element of Rn plus means x is in the cone Rn plus, that is x is greater than 0. This means that every component of x is greater than or equal to 0. Q is positive semi definite, and then this is a convex function which we are minimizing over the convex set Rn plus, which C is now Rn plus. Now, x bar is optimal if the gradient of this at x bar, which is q x bar plus c times x minus x bar, is greater than or equal to 0 for all x in Rn. Now, if you put x is equal to twice of x bar, which is obviously in Rn plus, because x bar is optimal solution, right. X bar is optimal means x bar is in Rn plus. So, twice of x bar is also in Rn plus. So, x is equal to twice of x bar, we set this particular x. So, this would imply q of x bar plus c times x bar is greater than or equal to 0. Now, put x equal to 0. So, from this equation it will imply that q of x bar plus c, putting, I am plugging in, first I plugged in 2 x bar here and then plugging in x 0 here, I will have minus x bar greater than or equal to 0, which implies q of x bar plus c into x bar is less than or equal to 0. So, if I call this as A and call this as B, so A and B combined will give me q of x bar plus c of x bar is equal to 0. Now, what do I get from here immediately? From this condition, which you will immediately show me q x bar plus c x is greater than or equal to q x bar, sorry, plus c into x bar. Q x bar plus c into x bar is nothing but this is equal to 0, which you already know. So, what you get, q x bar plus c x is greater than or equal to 0 for all x in Rn plus. So, this because this is true for any x, because we are just breaking the inner product and pulling one to the others. So, this would immediately imply, because this is true with every x in R n plus, q of x bar plus c is also in R n plus. So, process of finding a minima of this quadratic programming problem or QCP, quadratic convex problem, is to find x bar such that x bar should belong to R n plus, q x bar plus c should also belong to R n plus, and q x bar plus c inner product with x bar is equal to 0. This is called the complementarity condition. So, this problem is called the linear complementarity problem and has huge applications in many different areas and is very well studied, and still people are looking into this. So, you see that just from that simple optimality condition we have developed, we have got some quite new and interesting information. So, with this we stop here, and tomorrow we will talk a bit more about what happens when the convex function fails to be differentiable, a question which I had asked you. So, you till the next lecture you just think how will you handle this situation, and then we can speak about it in the next class.